Okay, so today's subject, we're going to focus in on groups. So I want to get the definition of a group back on the board. Start. Now, definitions, of course, have context, so we're really saying an algebraic group. We start with a set. We'll call it A. Along with a binary operator. Which we defined before. That's a map, and we use the symbol star for our binary operator from A cross A to A. So notice in particular, a group only has one binary operator. We don't need two, we don't have two. So this is a very general thing, but this binary operator has to have three characteristics. And I'm going to list characteristic 0, the 0th one, is really implicit in the definition because this is a map from A cross A to A. The answer is all line A, but we're going to list this one first because we'll need it later. Closure simply means whenever I operate on two elements. That is, A, B are in my set, then I must have the answer in the set. We'll look at counterexamples to that later. So that's really implicit in the definition of the binary operator, but it's good to make it clear. And then what else do we need? The fundamental property we need is associativity. And that means for all A, B, C in my set, I must have what? I need A star the quantity B star C must be the same as A star. The quantity A star B starred with C. That is, I can freely decide which operation I do first without changing the order. And both of these are really for all, right? If for all A, B, we need that. So associativity is really the fundamental principle. It's not that easy to obtain in general. What else do we need? There must exist an identity in the set such that whenever I operate any element, take any other element, or including this element, I need A operated with the identity must be A, and that must be the same as the identity operated with A. That is, the identity is the thing that doesn't change the input. A operated with E gives me A, and E operated with A must also give me A. Notice I didn't require commutativity with this operator, and I'm not going to. So this is a special case. That's why I have to state that the identity works on both sides. And then number 3, everybody in A, what do we need? Following our previous discussion. I have an identity, I have associativity. For everybody I need an inverse, right? So there must exist a B in A with the property that A star B is the identity and B star A. Inverses must work on both sides as well. So those are the 3 defining properties of a group. A set with a binary operator, where the binary operator is associative, there exists an inverse, and there exists an identity, and everybody's got an inverse, so we can label these as identity and label this as inverses. That is, everybody has one. Okay, now in addition to these properties, we have a fourth optional property that for every AB in the set, A star B equals B star A, commutativity is optional. So if we have properties 0 through 3, we have a group. If we have the fourth property also, optionally, we call it a special kind of group, a commutative group, or an abelian group. After Niels Heinrich Abel, who was a Scandinavian mathematician who did some significant work. And interesting, it's usually not capitalized, unlike Gaussian and other. Abelian is usually lowercase. Okay, so that's the raw definition of a group. If I need these properties to have a group, and in addition, if the operator happens to be commutative, that is, every pair commutes with itself, then we call it an abelian group. Okay, what I want to start doing is giving some examples and some non-examples that will make this clearer. But why do we care is the real question. And the reason we care is this is real abstract. That's why they call it abstract algebra. If I can find any set and any operator that behaves this way, then anything I prove using only these properties works for everybody. That is, for example, two things we're going to prove today is that the identity, if there is one, must be unique. There can't be two different ones. And there can't be two different inverses. We can prove that using only the group properties, and now we know it's true for everything we call a group. This is the idea of abstraction. Right? We prove it in general, and now it applies to lots and lots of cases. So first I want to go to the lots and lots of cases. What sets and operators behave this nice way? So we'll look at group examples, and we'll start with the prototypical one more time. We had it on the board on Monday, but let's do it again. And we'll do non-examples as well. If I take the set of integers z along with regular integer addition, is it a group? Is it a group? I need to test my four things, right? If I add two integers, do I get an integer? Sure. So it's closed, right? Is it associative? Is addition of integers associative? Sure it is. It's really hard to prove, actually. We almost have to assume that. So associativity. That is, a plus b plus c is the same as a plus the quantity b plus c, right? So we have associativity. And I guess we can say a plus b. If I add two integers, I get an array. What else do I need to be grouped? I need an identity. What's the identity for addition? 0, sure. So a plus 0 is certainly a, and that's the same thing as 0 plus a. it works on both sides. Right? So 0 is the identity in the additive group. And what else do I need? Inverses, right? So, and I write it plural because everybody needs an inverse. So what do I add to A to get the identity?
Negative A.
Negative A, right? Negative A is really a symbol for the additive inverse, right? What's the additive inverse of negative 3? 3, right? So if this is negative 3, negative of negative 3 is 3, right? So it always works. I'm done. I have a group. It's closed. The operator's associative. There exists an identity. We have inverses. Everybody has an inverse. What's the inverse of 0? That's always true in a group. The identity is its own inverse. Is it an abelian group? Sure. Also, A plus B equals B plus A. So Z is an abelian group. Okay, let's look at a non-example that's closely related. The integers with multiplication. Let's run the properties. Do I have closure? Yes. Right? A times B is certainly an integer if A and B are integers. Right? Do I have associativity? Integer multiplication. Sure. Do I have an identity? What is it? Integer multiplication. 1, sure. So I have an identity. I'm almost there. Do I? Yeah, you do. Okay, how about inverses?
No.
No, that's correct. Equals 1. Two times b equals 1. That equation has no solution in Z. Right? I can't go outside my world to find solutions, right? So there's no integer multiplied by 2 that gives me 1. So there's an example where I don't have inverses, because inverses have to multiply to the identity. So this is not a group. And the lack of inverses means I can't solve equations. That's why I really care about inverses. So solving integer equations is really hard because I don't have inverses to cancel things. So this is one reason I care whether I'm in a group or not.
What's the difference between the star and the multiplication sign?
I'm being lazy here and using star because of multiply.
Oh, okay.
It's sometimes used. I could use the X, but here it means multiply.
Okay.
Good question. Okay, let's look at another example. Without changing much. I go from the integers to the rationals, let's see if things change. How do we look in the rational numbers with addition? We have closure? Sure. I add two rational numbers, I get a rational number. Is addition of fractions associative? Sure it is. I can prove it, assuming that integer addition is associative by my rule, right? If I do a over b plus c over d plus e over f, and do the algebra, I can prove directly that that's the same as the quantity a over b plus c over d added to e over f. Just by assuming that integer addition is associated and using the definition of addition of fractions. That's not a hard proof. Is there an identity for integer, for rational addition? Sure, 0. Works on both sides, right? Do I have additive inverses? What's the inverse of a over b? Negative a over b, right? So we have a group, and it's abelian. Essentially, Q inherits all the nice properties. Directly from the integers, because we're really doing pairs of integer arithmetic.
Couldn't you assume we automatically have the commutative property from the associative property?
No. Associativity doesn't let you change the order.
Okay.
It only lets you regroup. Matrix multiplication, for example, is associative but not commutative. Good question. How about the rationals with multiplication? Do we have closure? If I multiply two fractions, do I get a fraction? Sure, right? A over b times c over d, by definition, is ac over bd, right? And that's a fraction. So we have closure. Is fraction rational multiplication associative? Sure it is. Right? And you can prove it the same way. A over b times the quantity c over d times e over f. That's the same thing as doing the multiplying the first pair, and for the same reasons. Is there a multiplicative identity in the rationals? Sure. 1, right? Which is actually 1 over 1 as a rational, times anything. A over b is a over b. And the same thing on both sides. So the integers are a subset of the rationals when I consider the integers as n over 1, right? Rationals are really pairs of integers, but when the second one is 1, I get the... Now what about inverses? What do I multiply a over b times to get 1? B over a. As long as what? As long as a isn't 0. But if a fraction has the numerator as 0, what is that fraction? So the answer is not quite. All but 0. So it has to be everybody, so this is not a group, because 0 has no inverse. That's the problem with multiplication in general. 0 is a special case. I can't solve equations with 0 in them because I can't divide by 0. And that's true in the... So this isn't a group, but it's almost a group. Anyone see how to turn it into a group? The only operation I have for a group is the operation, right? Can I fix up Q so that it will be a group? Oh, what's the problem? Can I throw it out? As long as 0 is not in the group, as long as 0 is not in the set, am I still closed?
Mm-hmm.
Do I ever multiply two fractions that aren't 0 and get 0? So I'll never get 0 as an answer for multiplication. It's still associative. The identity still works. And now everybody has an inverse because I've thrown 0 out. So to fix this, all I do is get rid of 0. This is a common trick to get a group structure. So Q, once I throw the 0 out, with only multiplication, is a group. So if I make that little adjustment by deleting 0, it never comes back, is the point, right? Because if I have two non-zero elements multiplied, I never get 0 in the rationals. Okay, one more example. The symbol for this, by the way, before we leave it, is actually Q star. We'll see that again later. It means everything that's invertible in Q. And we can play this trick a lot. And we will as we go forward. Okay. Let's look at one more example, and then we'll take our little video break and talk about the homework or the quizzes. So one more example. The set of all invertible matrices of a fixed dimension, square, right? This is a nice thing. So I want to consider this set with matrix multiplication. See, now my star isn't multiplying anymore, it's matrix multiplied. You know. So let's test it. If A and B are both invertible matrices, is the product invertible? Now you have to think. A and B are two invertible matrices. Think back to 260. Is the product invertible? What is everything we know about invertible matrices? What's the determinant of an invertible matrix? What's true about the determinant of an invertible matrix? It can't be 0. What's the determinant of the product of two matrices? Product of the determinants, right? So if the determinant of A is not 0, and the determinant of B is not 0, the determinant of C is the product of two non-zero numbers. So its determinant is not 0. So the product of invertible matrices is invertible. Right? And if I multiply two n by n matrices together, I get an n by n matrix. So yes, the product of invertible matrices is invertible. You can prove it actually. What do I multiply by AB to get my identity? We'll hold that problem for a minute. Is matrix multiplication associative? Does that work? For matrices? Sure does.
They're all in by n, right?
They're all n by n. Yeah. They have to be squared for that to work, right? To be invertible, they have to be squared, right? Yeah. Matrix multiplication is definitely associative, even when they're not squared. That's something we proved back in 260. Matrices are going to be an important example of this. Identity. Do we have an identity for matrix multiplication? What do we multiply by matrix to leave it the same?
I do.